a press maintenance webinar. I'm Lisa Jursenko, glad to be with you today. We have some very distinguished presenters, very popular presenters with us today. Just to preface, most of you probably know that we were going to have a live SAT. Dan Dunn of Castool Tooling Systems and Richard Dickson of Hydro. Just a quick note, everyone is on mute. So if you have questions during the webinar, please choose the Q&A capability from your toolbar, type your questions in there, and our presenters will be glad to answer those questions at the end of the presentations today, if we have time. It's gonna be kind of a long one. It's gonna probably go till about 3 o'clock. So stay with us and feel free to ask your questions. If we run out of time, you can always contact any of the presenters or myself, and we'll see that your questions get answered. Just quickly, before we get started, I want to tell you all a little bit about the presenters. David Turnipseed is a 30-year-plus veteran and third-generation family member in the aluminum extrusion industry. He has over 20 years of experience in manufacturing and maintenance, over 13 years of technical sales and product development, and he's currently working with SAT, an Italian engineering company that is dedicated to design, production and installation of aluminum extrusion, surface finishing equipment, and packaging. His experience over his tenure has been in various trades of technology with involvement, in the processes and maintenance of casting, extrusion, finishing, paint, powder, and anodizing. And he's held positions in the multiple extrusion companies in roles from technical services to management. David has authored several technical papers for organizations, including ET, organized and hosted technical workshops, seminars, and webinars for AEC in the areas of maintenance and process control in the areas of extrusion and finishing. Extensive travel, both locally and globally. He visits production facilities, suppliers, and trade shows, enables him to provide support and recommendation on solutions on the most up-to-date practices and technology. Dan Dunn has worked in the extrusion and die-cast industry for over 35 years. He's worked as a die man, press operator, stretcher operator, in roll correction, packaging, fabrication, and production control before he joined Castool 24 years ago. Danny is the director of sales. He is responsible for the global sales of tooling and equipment for Castool. This year at the annual meeting in San Antonio, we were excited to award Danny the Volunteer of the Year Award for his extensive commitment to AEC, the industry, and his sharing of knowledge. Richard Dickson has been in the extrusion business for almost 35 years, formerly with Alcan, and for the last 20 plus years with Hydro. He took up the post of Director of Customer Training and Development for Hydro Metal Markets after serving as Director of the Hydro Aluminum North American Technical Service Center for 7 years. He's been a very active member of the AEC Die and Tooling team and the ET Seminar Committee. He serves on several Aluminum Association and AST on technical committees as well. He has authored and co-authored Hydro's die design and manufacturing manuals, and as the leader of Hydro Aluminum's international die team for many years, he drove the effort to create and refine ever more productive die designs. Richard's passion remains advancing extrusion beyond its current limits through understanding and education. Richard is also a past recipient of the Volunteer of the Year Award as well. His involvement in ET, the committees, the events, and webinars, Richard is an outstanding member and well-deserved the Volunteer of the Year Award. Okay, I'm going to stop talking now, and I would like to turn over the webinar to David Turnipseed.
Hey, good afternoon, everyone. And I want to give a big thank you out there to all of you that are tuning in, as well as my colleagues that are helping host this webinar, and especially to Lissa that does a great job of putting all this together that none of us could do without her. So I will open up the first segment. We have some interesting information today, and we are limited on time, unlike a workshop. So we wanted to kind of highlight some of the priorities and some very important things that hopefully we can bring to you, and you think they're somewhat have some valuable interest in your organization. So I am my first segment will be based on 3 items, some partial items on safety, which we like to look at as the first priority, some preventive maintenance tools, and some troubleshooting tools. So as we always try to do, whether any type of presentation we're given, we always try to put safety first and show some of the things that we can all do to help safety in the workplace. And I highlight here within my slide, you'll see that the practice of the compliance of safety is always controlled by the leadership in each facility. I travel around to a lot of companies all over the country, and you see a lot of variance between companies that have safety procedures in place. So I wanted to point that out because it's not up to any organization, any government organization, any supplier. It's all up to how the leadership looks at safety within the workplace, and it follows on down to the employees. So there's many topics that we could talk about, obviously, with safety, but we don't have that much time. So I wanted to pull out a few out of some subtopics list. What we'll talk about today a little bit are e-stops, grounding, and exposure. And this all falls under some awareness, which is a big part of the safety in the plant. And we'll start with e-stop circuits, e-stop buttons. So more specifically here, the e-stop button itself. When the workforce is out around the machines, it is very important that the people be trained to know where emergency stop buttons are and what they look like, because when things happen, there is no time to try to analyze or figure this out. The areas we want to cover here of the layout and the identification is very important. And this e-stop button, this can make the difference in a second, whether it is somebody's life or damage to the equipment. So it's one of the most important, if not the most important item at a control station. So what should an e-stop button look like? We've seen many over the years. There have been some changes in regulations, changes in how people make them. I wanted to show a few slides at areas that I've traveled around the country and looked at different panels. Here on the left, you'll see a red mushroom head illuminated push button with a red label background. So it kind of stands out from the other buttons, but is it the right one? In the middle here, you see different buttons, but you'll also see a red illuminated button with a yellow background. And then in the far right, you'll see a red button with a label on it. So obviously, people, if you can read English, you can see that, but that don't make it the correct way to do it. So by code, here is the proper how the button should be. It should always be a red button with a yellow label to quickly identify out of all the red buttons or whatever you have on your panel that this is the compliance for emergency stop button. For you guys that want to go and check it, and unless something's changed, and I haven't looked here recently because I haven't been involved in it, but in the last NFPA 79 section, there is a regulation here under 10.7.3 that designates that the color of the button should be red with a yellow colored background. So now here are a few more photos, if you will, and you can examine for yourself. You'll see a panel on the left, and you see that it also has a red background with a red button that that is different, but if you've been trained that emergency stop buttons should have a yellow background, then it can cause confusion with somebody, and then they could hesitate. Middle button, this could be emergency stop button, it could be a cycle stop button, it could be whatever. So it's not really clear, and if somebody's got to make a quick decision, you know, it's really not suitable. On the right, you see a panel that is up to date, and it has a good, everything is set by code, and you can quickly notice that the button, regardless where the button is, with the red button and then the yellow background, when you're trained, you don't have to read, you don't have to examine, you can clearly make a distinction and hit. Another one here is just you have multiple buttons on the panel, but you do see the yellow background on it. So to start with, when you have equipment, whether it's been built in your plant or you bought it from a supplier, don't assume that the equipment has e-stop buttons, or they have the correct amount of them, or they are set right by our NEC, NFPA NEC code. Go and check them. Typically, for some systems, a supplier will produce designs within the electrical systems so that you can strategically place emergency stop buttons around your system, regardless of how big it is, where people are working, where you think that there should be a place where somebody can quickly hit an e-stop. So this drawing is showing what's typically done if the system is designed well, is to leave a jumper so that you can add on to the series circuit within wherever you want to in your plant around your equipment to add this on. And if it's a good design system, if you pull your electrical drawings, you'll see that. So I would closely examine that and do an audit and see if you need more. So even if you got all the things in place, you need some training. One without the other is no good. And all the personnel should be trained at where the e-stop buttons are, what they look like, and when you should hit them. But I would say here that you need to understand that the e-stop button is for emergency. So it's for emergency situation. Many times equipment is built with devices that have a lot of stored energy that need a proper sequence to shut down. So e-stop buttons, and I've seen so many times in the past that somebody don't take the time to sequence the system down, motor by motor or whatever, hit it and shut it down. And when this happens, you do a lot of damage to the equipment, whether it's stored in a large amount of spikes within the electrical system from high induction motors, items that need to cool down before they turn off, or whatever. So it's not to say that you should not use the e-stop button because of that if it's an emergency situation, but you should only hit the emergency button if it is an actual emergency. So you can go, and there's a lot more information in the NEC under the NFPA 79 that gives reference to all this detailed information about how things should be. So your electrical technician should follow up and make sure that you are in compliance, but mainly that the people and the equipment is set up in a safe way. So when you return, or when you leave the webinar or whatever, you should go and audit. This is a good flag to say, especially leadership, to say, hey, what about ours? Is our equipment correct? Are we doing our job to protect our personnel from danger out here, and have the right systems in place to shut the system down? And do we audit our employees to make sure, do we train and then audit to make sure everyone is trained and knows how to operate that. So that's it for e-stops. There's like I said, there is a lot more info that you can find out about it, but I just wanted to show some basic start of that. Next is grounding. Grounding is very clearly a safety issue within electrical systems. It is a way that devices are set up so that people are not electrocuted. And it's always best to have to follow the grounding rules, and we'll get to that. It's under the NFPA. So back on this slide, there was a question about how many amps does it take to kill you. There's some, you can look it up, and there's some under the OSHA. Many people think, well, it's got to be really high voltage or it's got to be high current, and that's not the case. You know, electricity is like hydraulics. You have a lot of pressure, which is a voltage, and you can have a lot of flow, which is a current, or you can have a lot of pressure that pushes just a small amount of current through your body and does serious damage. Under the OSHA government website, you'll see a listing here that I have on screen, and it's quite interesting. And it shows the different amounts of current. Now, it shows 1 milliamp is when you feel something. Now, 1 milliamp is 1,000th of an amp. All the way down to 100 milliamps is, in the right conditions, can be enough to kill you. And on higher, it's even more abrupt. So don't think that whether it's 24 volt AC or 110 or 480, 600, whatever, the likelihood of the higher voltage, you will, due to the resistance in your body, you will have less current, but the right conditions, you could have a lot of current with a lower voltage. So always keep in mind that it's a very small amount of current that can disable or kill you. So the systems are set up where things that need to go to earth ground can bleed off any stray currents to ground instead of through somebody. If you look inside a panel, you should see a bus bar. You should see green wires that go to the bus bar, and then there are codes about grounding that panel to earth ground, whether it be a ground rod or through steel that goes to a ground rod. So a good case in point is a motor that has a metal casing on it. You'll see in this photo that there is the current carrying conductors. This is a 3-phase motor that run into the windings. Now the motor internally is isolated from the case, isolated from ground. But if something wore, something broke down, something shorted, and it caused the windings or any other part of the electrical system within the motor to touch the case, then that case is also at the potential voltage of what's coming to it. Now, at times there can be no metal conduction to the case. You see this picture that has a seal tight to it, which is metal, but it could be the possibility that there is no metal conduit to it. So it's just sitting here floating as a metal. And that's another reason that the ground wire is there. So that ground wire, regardless of the motor, the base of it, whether it's sitting on vibration pads, whether it's isolated in any way electrically from ground, then that current, that short current can pass into this green wire and back to a ground source. If you didn't have that and it was isolated, then you may not know that something was at the voltage potential on the outside and it's just waiting for somebody to grab it and then give it a path to ground. So follow all the local grounding codes and the NEC, and they're very specific, and they guide you through how things should be. So when you finish or at some time at your next available PM or right away, go out, do an audit, let your people go out and look for any place where they see, whether it's an electrical panel, a motor, or whatever they can find that for some reason or another it was never grounded or it was removed or it some way has been altered that it don't have it, then and look for the path back to ground. That just because it's grounded at a motor don't mean it's grounded at earth ground. Further reference, you can go to your NEC Article 250, where there's a large section on grounding for almost anything that you would do. There's some exceptions, but almost anything that you would do in your facility, there are instructions for grounding. The next one is on the safety is exposure, and this is an item that sometimes is not put a lot of focus in, but I've seen some very dangerous conditions in plants. So sometimes people take the attitude that if it is lower voltage, if it is something that's not in somebody's direct contact at their workstation, that it's okay. However, these are terrible items, and these are pictures, and I would never embarrass anybody saying where they're at, because this happens at all places. And if you go and you look around your plant, you can always find something. So here, the one picture is a case of a switch that somebody probably had to check. Whatever they had to do to it, they left the cover off, thinking, well, okay, it'll still work. However, this leaves the exposure for somebody to either touch or some other element to get in there and short it out, or even just the atmosphere. The middle one looks pretty bad as well. It's like wide open. You can see it's three-phase, so more than likely it's 240, 480, or even higher. And it's just waiting there for something to get in it and be a major situation. And even a case where the panel, as you see on the right, is slightly open, you still open it to the atmosphere. So whether water could get sprayed in it, whatever could happen, it still can be just as dangerous. And just because it's cracked open a little bit, don't mean that it's okay and it's safe. Here's a picture of some switch gear. You'll see that some of the disconnects are guarded with a cage and with some handrail. And then you see on the other side some newer breaker panels that are not guarded. So I guess somebody maybe assumed if it's newer, it don't need to be. But either case, there are specific codes within the NEC for guarding of these. And the biggest, whether it's a forklift or whether it's somebody pushing a cart, anything can happen. And when you have centers with high current capacity like this, not only can you put in danger people and equipment, you can also shut your whole plant down when these main centers, if they were to get damaged from mechanical abuse or even any kind of abuse, really. Another one here, you see that a disconnect where there is a guard there, and you can go back and you look in the NEC, and it will show you specific practices or what's required, distances away, and what they should be. So again, when you go out and do an audit of your plant, start looking around for all these things that we talked about here. And you can very quickly make a list, and you can't get to everything immediately, but you can start working down the list, and every single thing you can do to protect your electrical centers like that is a preventative maintenance that not only will help you for cost and time down, but also could save somebody's life. So on the guarding, if you look under the NEC Article 110, you'll find a whole lot more about that, and it has very specific info about that. So that's all we'll talk about for safety, and there's so much to get involved in when you're doing that, whether it's arc flash, whether it's a lot more things within the code. This was just a few things at the short time we had that I wanted to highlight these. The next topic we talk about is preventative maintenance. And most people today, when they talk about preventative maintenance, it's more about, there's a lot of discussion about computerized maintenance systems, which are all good, but there's some basics, fundamentals of preventative maintenance that is also it's at the source, things that will always help you in the long run, regardless of how sophisticated your PM programs are. So we're going to talk about guarding here, but a little bit different way than on the safety. So out in your plant, on your equipment, you should try to make some kind of guard if you don't have it for all electrical and electronic components. 9 times out of 10, a failure is going to be either from some mechanical issue, whether it comes loose, or a lot of times it just gets abused and are damaged from abuse of things that happen around the area. So just a couple of ideas, guard for physical damage wherever a device can get stepped on, can get hit. The farther you go into guarding every item on your machine, the less problems you're going to have from failure later on from damage. Guarding from environmental conditions. Here you see on the right, you see a push button station, a remote push button station, but it has a very nice guard. And this was done not by the supplier, but by the plant, the people's maintenance that wanted to go to the extra step to make sure that where they had it, the location was guarded from the elements of rain or whatever. In the left, here's a picture of some conduit being held with some wrap that, whether it be cables or conduit, that you have a moving device. If you don't look at that very closely and make sure that it cannot get snagged or hit by something moving, then it's just, you might as well put it on the PM for repair, because it's going to happen. So it's good to always look for any area that you can have breakage due to moving parts. The picture on the right, it's on an extrusion line. So, with the hot extrusions, any insulation on any wire that can come in contact with the aluminum is going to be an issue. So look for any items that are close by, regardless if it what size extrusion is or whatever, it's all the same temperature. So anything that can happen where extrusion break, extrusion fall off the table, any area where you can have such high temperatures, you need to go to the extra effort to make sure they're guarded from high heat. A lot of physical damage. It could be encoders, what you see on the picture here, other devices, especially sticking out in aisleways, were either from passing by a forklift, other type of equipment, or whatever. They need to be guarded as much as possible. The picture on the right shows this is just an area of foot traffic, and I see so many conduits that are flat when I go into plants where people are continuously either walking or rolling steel wheel carts over and whatever. So if you go to this extra effort to guard whether it's cables or the conduits, then you're really doing a good prevention. And make sure you paint them yellow, because you want to follow the safety guidelines about something sticking up where somebody might trip. Just a few more pictures here of switch gear where some good guarding has been done, especially when if you have a hoist or cranes where loads can swing into them. Always be cognizant of a load that could hit. And believe me, I see a lot of electrical panels that have been hit by tooling. Another guarding is to be able to, for wiring, when you do have moving devices, to do the best you can for conductors moving back and forth, and copper, especially copper, tends to work hard real easy, and some other alloys do as well. Obviously you see a thermocouple there. Everybody knows what that is, and that can be one of the largest problems on a system of going back and forth and then finally breaking. And it becomes just a regular task to do this. So always look for ways to reduce the wires from moving back and forth. Picture on the right shows extreme condition of where some chemicals are in the area, and the electrical devices need to be in the proper NFPA or NEC boxes, and things protected from chemicals that can attack. Even something as slight as light interference. Here's a switch that I remember on a job where even though the frequency that these photo eyes are supposed to be looking at, there's all kind of frequency coming out of the sun, and at the right angle, the sun would interfere, make the switch, and then you'd have a issue on the control system not working correctly. On the right, this is very common. So much flex conduit is used in the plant, and a lot of times over time they get hit and then they're broke, and the metal inside the flex conduit is very sharp, so it can easily cut the wire. So these are things to look at and go ahead and start finding signs of these and do replacement and try to do some guarding for that to keep it from happening again. So when you go back out into your plant, look for all these areas that you could do a little bit better job of guarding. Even though if it has never been hit, that don't mean it can't be hit or damaged. So the enclosure, I want to talk just a minute on the enclosure. We're getting low on time, so I'll probably either just speed up a little bit or we'll stop a little bit early for the next speakers. The heat is one of the main enemies of the electrical components and panels, and as heat rises, then your devices start to degrade and fail early. Here's a picture of a panel with a good air conditioner on it to decrease the heat and humidity around the components. But if you don't manage the maintenance on the air conditioner, I pull so many guards off that the filters are so dirty, you're actually just putting hot air back in. So just because you have air conditioners on it and running, don't mean it's doing a job. It needs to have a proper PM. One prevention of heat inside of panels is to try to get all the heat, the items that generate a lot of heat out of the panel. Then you don't have to do so much to get the heat out of the panel. Here's a picture of some transformers on top. So they're dissipating. It's a different NEMA rating that can sit outside of the panel, but you don't have all the heat is put into the panel. All panels should have some way to remove the heat. Here's a simple, one simple way is to allow the natural convection of the heat that's going up, let the heat leave the panel, but it needs to be at the correct way. And I have seen even from people that made electrical panels and controls that were on wrong. So the proper way for the air to flow is through the bottom on one side and the top of the other, since heat's rising, and you want the cooler air at the bottom to go into the panel, go across all the components, and then out. You don't want it short circuiting and going out the same side, then you don't get any cooling effect. You pull heat out of the panel, but you don't cool the components. So when you go back, look for panels that are always running with the doors open, because there's an issue with heating. So the quickest solution to that is to open the panel and then you expose it to unsafe condition. The proper way is to go back and find out what cooling or why the cooling is not working, and if it don't have cooling, find a way to get the proper cooling. My last section right here, I think, is one of the best troubleshooting tools used. I probably wouldn't go into the plant to do any troubleshooting without one, and it's an IR thermography camera. These things the cost has gone way down, and they're so valuable to a maintenance department. So the thing about, instead of a temperature probe or whatever, the thermography, you can see different areas of heat, which you cannot see with a natural eye when you're seeing heat radiation. So there's a couple examples of some cameras you can buy. That should be as important in a maintenance tool crib or wherever you keep it than any other tool. It is so powerful to use. Just to give you a few examples here. Here is if you look at the panel on the left, Here's a wire on top that no way with your eyes that you could see that there's an issue of overheating. And and I tell people, and I probably should do it when I get back home, to find somewhere to look at in your home, because this is the #1 cause of home fires. This is probably where a bad connection is, and it's sitting there arcing all the time by not getting good contact, or it doesn't have a lot of surface area, and you don't have enough area there to conduct the amount of current that's passing through it. But when you take a quick look in a panel with a camera, you notice these things so quick that are issues or can be issues. Same way on the picture on the right, you see a bad fuse clip or loose fuse clip, and so you see ahead of time of something that's happening that you cannot see, and you don't want to be sticking your hands there, obviously, to check temperatures, and especially with power on, but you don't want to anyway. You don't want to get into the habit. Here's a motor that's overheating. When you look at the motor, you see the whole motor is hot. So with the range of temperature that you set for it, you can see from white down to dark, you can set the range. So that don't mean it's extremely hot. It means it falls into the range that you set. The whiter, the lighter the color is, the hotter the source is. So this gives you a good indication here that the whole motor is hot. Should it be? Well, here's a normal motor, a TEFC, meaning it's got a fan. It's totally enclosed, but it's got a fan on the back. And that fan, it pulls in ambient air in through the cooling fins of the motor. It may have cooling fins or may not, but it moves air across the motor to dissipate the heat. Eventually, if you don't, then this will be the culprit. I mean, mostly motors fail either from a bearing life or from heat, and generally it's bearing life, which breaks down the insulation and causes failure. So you can go quickly over your whole plant. You can look at any motor, and you can see quickly if something don't look right. Just some more examples, and it don't have to be electrical. The one you see here is an outdoor transformer, and maybe nothing's wrong, but you can go and take a snapshot of it, and then look at that once a 6 months, year, whatever, just to have a baseline of how things look, and then you can easily spot if something's wrong. At the bottom, you'll see another wire with loose connection. And then there's other things you can see too. You can see anything that's related to heat. So it could be a bad bearing somewhere. It could be a roof leak. It could be heat escaping around a door. The seals are bad. Here's some more examples of what I'm talking about here. So this is the most powerful arsenal that maintenance people can have, is to just see things they can't see with their naked eyes and do quick checks. Now here's a motor I found that is completely stopped up on the fan. I didn't have the thermography camera when I had it. If I did, it would probably all be white, because I went over just to check the temperature on it, and it was so hot you couldn't even put your hand on. If you didn't do that, you know, people are walking around all the time thinking, oh, the motor's okay, it's built up, but it's okay. Well, that's not the case, but you can see it with the thermography. So check in to see whether you can rent or buy. They're a lot cheaper now, and you can save so much money, and you can do so much good with thermography. I think it's just the #1 tool, like I said, that you can have. So, and there's other things that you can do to prevent some of these cases where I show some filtering and all. So I want to turn it on over. I have some more information about diagnostics and documentation, but since I'm out of time, and I'll be glad to share the presentation part of it with anybody that would like to see the remaining of it. If you email me, and I think there's some good things here. So Lisa, I'll go ahead and turn it over to you to turn it over to Danny, and I appreciate the time. And this is the first time I have done this with a live picture. We're all doing this, and I would like to have your feedback, because I think it makes it a lot more personal and enjoyable. Maybe you don't like to see us, but whatever you think, let us know, and we'll keep trying to make these presentations better.
All right, so we're just waiting for this to pop up. David, thank you very much for your information. Let's see, can we see my screen yet? Hold on one second. screen. Come on. Takes a little while to fire up. Let's see here. How's this? Come on, keep going. There we go. Can you see it?
Yep.
Perfect. Okay, which screen are you seeing? You're seeing the starting screen?
Press maintenance webinar in presentation mode. You're good to go.
Good to go. Thank you very much for that, David. Thank you very much for your information. I'm going to leave my webcam on, just seems like a cool thing to do. So thanks a lot for the time. Thank you very much, everybody, for logging in. I'm going to be covering press tooling, but I actually took a little bit different approach to it as I've done this several times with my distinguished presenters here. I want to look at an evaluation of each of the components, and I want to look at it in this way. So if we look at the dummy block, cold cleanout block, stem, shear blade, container, liner, assembly, and liner. I want to start first by saying something that it was a quote that was told to me by a very predominant extrusion maintenance manager, actually. And he said that the maintenance techs today are much more than people who keep the machines running. And it was so profound to me. People are called wrenchies, or they're called electricians, or they're called whatever it is, but maintenance techs are much more than people who keep the machines going. And that kind of inspired me to take this webinar down this path. So follow along with me. If we look at the individual cost of tooling versus the operation, and by that I mean the cost of the operational performance far outweighs the cost of the component. So what is the tool's time to failure? Whether it's a container or a stem or a block or a shear blade, you should have a reasonable expectation or a reasonable framework of what you believe that tool should last. What is the cost of the repairs of that tooling versus new? What is the tool's life after the repair? Does the repaired tool have a reduced life or limited life, and will it contribute to unscheduled downtime? So if we break that into 4 categories, we look at time, contact efficiency, recovery, and speed. So time, does its diminished function affect unscheduled downtime, scrap, or productivity? Contact efficiency, does the tool's diminishing function affect contact efficiency and recovery? Does the tool's diminishing function affect recovery? And ram speed, again, does the tool's diminishing function affect ram speed? Everything has a life. Not everything is like a fuse. Either it's on or it's off. It starts to wear out, and as it starts to wear out, at the end of the day, we're all trying to reduce what we call unscheduled downtime. And unscheduled downtime is something we're always chasing. So let's start with the dummy block first. The dummy block's function: to repeatedly transmit the force of the ram at high temperature to the billet. Simple. Expand quickly under load and maintain a secure seal with the container while leaving only a thin film of alloy in the liner. Now, I'm going to cover that a little bit more in the next few slides. To cause no gas entrapment that can result in any blistering, and to contract immediately at the end of the cycle, so that way when it pulls back through the container, that you're not pulling any of that precious aluminum skin out of the liner. It can compensate, depending on design or float, for minor press alignment. It has to be quickly and easily removed and replaced. Again, if there is some unscheduled downtime, man, this cannot take hours to do. And to function effectively until production run is complete. So let's look at that, because I'm a visual learner and I like to share a little bit of video action. So what we have here is a video that I'm sure many of you have seen I've played before. It's a container liner assembly. You can see billet is collapsing as we'd like. It relaxes, We have our gigantic burp cycle, and then we extrude. Pretty simple. I'm going to stop it there. Now, when we look at the dummy block's interaction with the liner, this is very critical. And as we fly around and we all move around and we see extruders that are moving from 3,000 to 5,000 to 6,000, even to alloys into the 6082 or 7,000 or 7B04, some of these high tensile, high iron alloys, it's all about extrudability. And by extrudability, we mean the size of the gap in which that the alloy can be extruded. On the die-cast side of our business, we did a very important article, and it was called the Faithful Fourth Thou, which means molten aluminum in the die-cast industry and automotive structures can flow through fourth thou. So when we talk about tooling clearances, we talk about the Faithful Fourth Thou. So how do we manage clearances in die-cast to make sure that we don't get larger than fourth thou, because then we get blow-by, which is similar to extrusion. So when we look at this, and you can see my mouse on the screen, 1 to 3,000 series alloys, this is the typical clearance that we would use on our tool. 6,000 series alloys, this is the clearance. And again, it has to do with extrudability and what minimum size gaps that the alloy can pass through. Ergo, that's why when you use microtubing, you're using a softer alloy, because the softer alloy has an easier extrudability. When we look at that function again, because I just like to show a video, again, it's very important that as the block expands, it gets into this area and then leaves that small gap between the OD of the block and the ID of the container. Maintaining this gap throughout the cycle and at the end of the cycle as it pulls back is extremely, extremely important. Why? Let's get into the why. That aluminum skin thickness that's inside there, under temperature and pressure, as the liner starts to expand, which it does,
I don't need it all.
we want, sorry, are we good?
Okay.
Are we okay? Yeah? Okay, I thought I heard something, I'm sorry. You can still hear me, can you, Richard? We're good?
Yes, you're good.
I just didn't know if I lost anybody. So anyways, to back where I was, let me look through my cards. Oh yeah. So as the container either thermally and mechanically expands, we want to have a controlled amount of skin thickness that remains the same throughout the cycle. Okay, so what's very important is that the skin thickness varies throughout the cycle. That means that we could introduce aluminum skin into the extrusion, which will show up as pickup on the extrusion. So if we have this poor interaction here between the ID of the container and the OD of the dummy block, we'll start to see blow by like this. So if we have the interference clearance, which is basically an oxymoron, means that the dummy block is making 100% contact with the ID of the container. This is the type of blow-by damage that we'll see, and it's just basically combustion ignition, which also will show up on the face of the container. Now, I've got a video here showing some entrapped air, and it's a shame that you can't hear.
Let's look at one more.
Fast forward it. I know some people have already seen this. You'll see as the billet is upset inside the container, we're actually going to have compression ignition inside the container. If we have any oil leaks, whether it be off of the log here or off the ice here, that will also contribute to help this ignition under compression in the container, which causes a tremendous amount of damage on the die face as well as the face of the container. Let's talk about welding of tooling. I'm going to show you one of our dummy blocks here that's been welded, and sometimes with the best of intentions, we have an error. So, you know, the welding of tooling is something that for Castool we've never been a really big fan of, and it has to do with 100% to do with performance and safety. This was one of our dummy block rings that was welded by somebody who was trying to, you know, save a little bit of money. But what happened is once the two-piece billet got cocked on the loader, The dummy block was then pushed to the side of the container and hit the side of the container and broke this piece off. So this was the piece of weld that came off, and this is what was left. Now, what's really tragic about this piece is you can see some discoloration from here to here on this welded piece. This was actually went approximately 30 yards across the extrusion plant and hit a maintenance technician in the leg. Not only was there some damage done to this person because of the sharp piece of steel flying across, but the fact that it was over 800 degrees. So it was something that really was brought to our attention because it was our tool that it happened to. But then after further investigation, we found that the part was welded. So something to take into consideration in your overall evaluation of things that you're repairing. We talk about release agents, graphites, and those types of things. It's important. If you're looking at graphite or any flammable toxic fumes can also be put into the air. They're dirty. They're extremely dirty, as well as they can be considered a carcinogen. If we don't minimize its use, then we can create blisters and holes up in the profile. If we're going to use any electrostatic type of equipment, it's really important to make sure that we check all the grounds, check all of the desiccates that are used in there for making sure there's no moisture in the air to prevent clogging. And the number one rule that we like as far as any kind of a release agent lubricant, more is not better. Now, I've got a video here I'm going to play, and you won't be able to hear it, but at the end of the separation here, right, there is a ginormous, if that's a word, clink as the mandrel is being stuck to the butt. I had to go to this customer because they were pulling dummy blocks apart. And then upon further investigation, when I was there, we found that there was no lube in the lubrication system. So again, just a little quick PM, make sure that stuff is, everything is functioning. When it comes to the dummy blocks, it's really important to have yourself a checklist. Pull the dummy blocks if you can on a regular PM once a week. Now I know that sounds excessive, but if you're blessed enough to have the press or any type of maintenance downtime scheduled maintenance downtime, it's important to take the dummy block off, check it, run it through, check it on the X and Y axis, plot and chart the OD of the dummy block. Make sure that you're sharing that with your dummy block supplier so you can start to see if the dummy block is starting to reach its permanent deformation.
Hey,
The
Danny.
reason why I like to do it during a regular PM is, again, staying away from unscheduled downtime. Changing the dummy block during a scheduled downtime doesn't cost you anything. Changing it while it's clogged or not functioning on the press, an average press time will be anywhere from $1,000 to $2,000 an hour minimum. Average cost of a dummy block might be in the $1,000 range for your small to medium sizes. The moment you have to stop that press for an hour or an hour and a half, that just exceeded whatever the cost of that dummy block was. So it goes back to the diminished life of the block, and as its life is diminishing, how does it contribute to unscheduled downtime, recovery, and all those types of things. So when we look at it on a chart in sizes of permanent deformation, if we start to chart the OD of the dummy block as we take it off, and we look at 1 millimeter of deformation, 2, 3, 4, 5, we'll find that when we get to a certain size, say at 3 millimeters on our block, you'll start to see back end blisters happening in the block. What you're trying to do is elongate this time. So this has to do with maintenance, lubrication, and block design, making sure you have the appropriate block design for your application. We're trying to move it from here to here, and with good practices, it can be done. So I'm going to move on to stems. Stems are very important for a lot of reasons. Their goal or their job is to transmit that force from the main ram cylinder to the dummy block. That connection is extremely important. When you start to see some buildup, uneven buildup on the block, you can probably start thinking about alignment, especially if it gets back up onto the stem. Very highly compressive tool. I'm going to show you a thermal image that is going to support the importance of stress relieving. One other thing that's really important Now this is a sample photo that I took in the plant, and this is the flatness of the back of the stem. We had a customer that was breaking some stems and breaking some dummy blocks. So of course, you know, we start looking at everything. Once we pulled the stem off, we found that the outside 1 3/4 inches of this back of the stem was not making any contact with the pressure plate. Once we pulled the pressure plate, we found the pressure plate was coined. The problem with that is, if the rear pressure plate that's located in the back of the stem, if unchecked, it can, during regular maintenance, over time the plate will get distorted. Under pressure, even if the press is aligned, the stem under load will move. So if we take a look at that stem that was offset or pivoting on 1 3/4 inches, like back in slide 15, if that stem slides over 40 inches, it's going to make contact with the stem or mixed in with the liner. That axial pressure is going to put that pressure at the stem end of where the connection is with the block, as well as midway down the stem, as in Richard showed with Richard's going to show you in one of his slides. I gave it away. So look at this stem. This is when, before we pulled it out, there is an actual crack on the 3 o'clock position of the stem that was absolutely being side loaded by the housing and the container. Remember, that container and the container housing is sitting on 4 axes. It probably weighs accumulatively between 50 and 80,000 pounds. The average 8-inch stem weighs about 750. Stems are not designed, they are designed to have column pressure. They're not designed to have axial pressure on them. So if we look at where that is located, I'm going to just go through that. But quickly, one other thing I wanted to put in here is at the same time, if you're pulling the stem and the holder and the stem pressure plate, which is located back in behind the stem, check the platen pressure ring. That's the pressure ring that obviously you know that are located in the platen. Do the same thing. Check that for flatness. Make sure it's square. Make sure that it's true. Because if not, now that die has the opportunity to pivot. And under pressure, it'll pivot. Stress relieving. This is a thermal image of a stem that I took a little while ago. You can see the front end of the dummy block is 820 degrees Fahrenheit, 465 just behind the connection, 270 3/4 of the way down, and back here it's actually about 85 to 90 degrees Fahrenheit. Pressure and temperature over time will work harden the front of the stem. Most stems are manufactured 46 to 48 Rockwell. We have seen stems come back to us for stress relieving at 60. There is a calculation for doing that we came up with years ago, and that's based on the column strength of the steel. So we don't see many presses that are over 130,000, but when we put this together, we did this based on a solid piece of steel. So if we look at most presses that are running at less than 100,000 PSI, now that's on the face of the dummy block, not the face of the die. That's two different things. If we have a 40-inch long container pushing on an 8-inch die, the pressure on that is approximately 94 to 96,000 PSI on the face of the dummy block. If we then take that same 8-inch container and we make that container now 52 inches long, that 12 inches longer of container takes the face pressure on the dummy block up to 104 to 106,000 PSI to the face of the block, but still remaining at that 94 to 96,000 on the face of the die. Reason being, the increased pressure that's required to push that billet through that longer container has to be done at the push end of the press, which is not translated to the face of the die. So be aware of what that is. Try to keep this as part of your PM schedule and stress relieving the stems. Let's talk about butt shear. The dead metal zone must be sheared off from the die before the next billet is loaded in. Properly designed and maintained shear eliminates blisters, reduces surface contaminations, and it eliminates flaring due to smearing that gets caught across the die, like you can see in here. This here will contribute to container tilt, which will contribute to flashing, which will contribute to unscheduled downtime and productivity issues. Here, the operation of a butt shear. The shear must separate cleanly and not stick to the shear blade. How many times have we seen this? shoot it again, lower, cool, lower, lower, up, lower, just to make sure we shake that butt off. At the end of each cycle, the butt end must be removed from the die face as well. The shear face must remain free of distortion and present for the clear for the next billet to be put in. And I'm going to cover in the next couple of slides what some good guidelines are for clearances. Next, to ensure that the material is not drawn out of the die. We cannot have the shear pull material out of the die. If you look at this video I'm going to play, you're going to see it's going to shear. Look what happens. You've seen it 100 times. Stop. Whoop. Got to go back. Sound effects and all. Need to keep this going here. Stop. You can see now the shear is returned back to its park position. And the container, if that container closes on this butt, I think there's enough people on here that have seen this once or twice. You can actually see it's happened here. There's flashing. What'll happen is the container will not completely close. They'll load the next billet, and we've got a holy hallelujah, get a hold of maintenance moment. Uh-oh, uh-oh, uh-oh. I don't like that whirly. There we go, lost it. Hold on. I don't know what happened. Are you guys all still there? Everybody,
We're here, Danny.
or did I lose you?
No, you've got us.
Okay, now I'm going to go back to where that was. Hold on. I wish this was more interactive. I wish somebody could just say, you're going too fast, you're going too slow, we don't like it, blah, blah, blah. Okay, here we go. So this is where we were. Shear blade clearance. From the die side, the die face must be controlled. Ideally, 25 thou. Too much clearance is going to leave too much aluminum. Even if you shear it straight, there's going to be too thick of a wafer of aluminum left on the back of the die, which will then now smear and pull back up or down, and then it'll start to build up on the container seal face. This will contribute to a problem with recovery. There has to be a good seal between the container and the die holder. It's important that the discard again is removed cleanly. Typical values of clearance between the shear blade and the die from 1 millimeter to 1.2 millimeters or 40 to 50 thou. So again, work with your tooling people, work with your technical people, find something that you're going to work with, and then just monitor it. When we look at a shear blade malfunction, this is what we're talking about. Build up down on the bottom and pulling the material out of the die. When we start looking at pulling the material out of the die, this is what we're going to typically see. Again, we've got a die, a bolster, backer. This is getting a little bit more into the inside of the die of what we see. We see that material getting pulled out here and here from the die. The next billet gets loaded. There's our wonderful burp cycle. I'm just going to stop it. This air right here only has one place to go, and none of it is positive. The air trap that's inside there gets into the ports, and it may or may not all come out now, and it ends up on the extrusion. We start to see this damage on the shear blade. Again, this is the reason when we start talking about the diminished life of the tool, does it affect downtime? Does it affect unscheduled downtime? Does it affect recovery? Yes, it does. When we came out with a two-piece shear blade, we didn't come out with a two-piece shear blade just so you could replace the tip. We came out with it because we know how much time that it takes to shut a press down to pull off the shear blade to replace it. So what we find is that people were going longer periods of time running with a shear blade like this. But if you could take a shear blade off and replace the damaged end in a few minutes, then you're going to do it more frequently, which means now you're not going to have issues with any unscheduled downtime is going to be kept to a minimum. So again, here's another picture where metal is being pulled out. This is not die design. This is not alloy. This isn't anything other than, procedure. Again, we see a poor shear and we see a good shear. All shear blades are not considered equal. You cannot use the same type, or you should not use the same type of shear blade that you would do for super soft alloys as you would for hard alloys. A 6063 butt in 9-inch is a different size than 6061 butt in 9-inch. So you can't expect the shear blade to be able to shear it off and not pull metal out of the die. So when you start looking at shear blade designs, and maybe not, that's not something that maintenance looks at, but if maintenance is going to start seeing this, they're going to start seeing blisters. They're going to be, people are going to come after you saying that the shear blade or the shear is not aligned. You can actually have some ammunition in your back pocket that says, do we have the right design for the alloys that we're running? Some extruders were running nothing but 6063 for years. Then they started running 6061. Then they started running 6082, still trying to do it with the same tooling. Let's talk a little bit about containers. I'm going to talk about standard containers that have wraparound heating, and then some basic checks and things that you should look for on internally heated containers. Again, it's really good to have your own maintenance form to start looking at the containers themselves, how they come in, get that information from your suppliers. Every single supplier that's out there has a very good quality system. They'll be able to supply you with that information. Just don't get inspection reports that say complies or that the bore is 7.375. 7.375 what? Minus nothing, plus 1 thou, 2 thou, 3 thou. It's very important to know that. We're dealing with precision tooling now. We're not just making simple profiles. Have your own internal checks. Have your own form. When we talk about hardness checking a container, it's not rocket science. There's no special wheel that we use. It's just a strategically placed checks on the container, and they're repeatable. We get a regular grinder. We grind them all off a few thou, making sure we take away any of the oxides, but we don't do it too much where we're going to work hard on the surface. So it does take a little bit of touch, but work with your suppliers, monitor that stuff, keep track of it, and track the life of your containers. Don't just get a simple, yeah, it's good. You're going to know as the life of this container starts to move. If we supply a container from, say, for example, 32 to 34 Rockwell, and it's supplied through here, and it's 34 Rockwell on an average. If we all see the container start to look like this, it doesn't go from 34 to this in a day. What'll end up happening is you'll see 34, 28, 34, then 33, 24. That is what we're starting to track as the diminished life of the tool. Is it going to affect unscheduled downtime, tooling life? Absolutely. As that container gets softer in the middle, it's no longer going to have the support in the body to support the liner. So some people will start to reline their containers when they see blow by in the dummy blocks. It's probably not the greatest indicator. Reduced liner life. If we don't take care of this, we're going to see that reduced liner life. Liners don't wear out. There's no contact between the container and the dummy block. We're going to have reduced dummy block life. We're going to see increased scrap, blisters, surface defects, lower productivity, lower ram speeds. All of this has to do with maintenance. Again, maintenance techs are more than people who just twist wrenches and keep things running. Again, just a little video as a visual to what's happening when we have a softer container. That container soft and bellied, every billet, and I'm sure Richard's going to cover it, has an inverse segregation zone, which is basically like a bark to the aluminum. That inverse segregation zone gets loaded into this area that's bellied out onto the container. If you're only ever going to push one billet, then you're cool. It's all good in the hood. But if you're going to continue to load billet in here, you're going to continue to compile inverse segregation zone from the billet into this bellied area. After 4 to 7 billets, 4 to 8 billets of this, we start to see that inverse segregation zone that was on the billet actually ends up going through the container, through the die, and ends up on the extrusion. Now, it doesn't all go through the extrusion. Parts of it will stay in the die. So that's why some people will call me up and say, hey, Dan, we've got a surface finish issue. Where is it? Well, it's front, middle, and back. Oh, no, it's just in the front. Oh, well, no, maybe it's just in the back. Well, it's intermittent. Intermittent. It could either be type 1 inflow, which any of that billet skin that gets into the die is going to park there. And it's going to come out whenever it sweet feels like it wants to. Liner face conditions. Again, With the amount of maintenance people that we all speak with, I don't know why that changed. The maintenance people we speak with, we see people in production or production control, which is a bit of an oxymoron. Moving dies. Let's move those dies from the 9-inch press to the 8-inch press, or the 8-inch dies to the 9-inch press. Just because the extrusion fits in the hole, that doesn't mean that that is what should be running on that press. The interface between the die and the ring and how it seals on the container is so critical. If the ring and the die infringe on the area, which is in most manuals, or you can talk to your die maker, your tool maker, that is going to teeter in here and chip away at this edge. As soon as you lose this seal, trouble with a capital T. We start to see flaring. So any of this visual damage that you see, again, if we start getting chipping away on those faces of the container, we're going to start to see buildup of aluminum on the face, which is going to, hold on, boom. See that container tilt? As soon as you get that container tilt, what happens? Right away, we've reduced that clearance between the OD of the stem and the ID of the container. Maybe on a 30-inch container, that's not a problem. Maybe on a 50-inch container, that's a problem. But at the either way, it's axial load on the stem and the block. Now I'll continue this. Watch as we go to extrude, look at all the aluminum coming out, and then we get our flowers. And don't get me wrong, I love seeing some of these things that are anodized and hanging in a plant, in a factory. They look really cool, but it's probably one of the biggest oops moments that can happen in extrusion. Storage of containers with heating elements. I don't care who your supplier is, all of the elements are built the same way. Internal wiring, MGO packing material, very, very, very important to keep them dry. If you let them get wet or they see that moisture, depending on how much you get, it can be catastrophic to the elements and the heating system. So it's really good to have a slow, dry heat. Check the mega ohms, get those numbers from your supplier. So when you do your own checks on site, if you've got less than 0.25 mega ohms or 250 ohms, they need to be dried out before use. If not, as soon as you put power to it, done, bang, you're going to blow the elements out. So you need to preheat those either in an oven with no power to them until you dry them out, and then you can slowly draw them up. Right here. Simple practical method to the elements is to preheat them in an oven. Shoot, use your material heating oven if you like, but you're going to have to dry them out until you can get those ohm readings the way that they should be. Wiring protection, check this stuff. Graphite, we're never a big fan of graphite grease on a press. One of the biggest challenges with that, especially with an electrical system, is that once the graphite burns off, or the grease burns off, the remaining graphite, it's thermally conductive. And it will cause shorts if it gets into the electrical system of the container. If you're going to have the types of system, take a look and see if you see anything visual. You know, when you go get your oil change at a quickie lube place, they just like to walk around the car, flick your lights, blink your lights, some of the simple things. You know, we want to look to see if there's any broken TC connections, cold junctions, wire frays, loose connections, loose element leads. Those types of things are going to contribute to unscheduled downtime, and that's what we're trying to avoid. Look for visual cracks. Step one of making sure that we don't have a catastrophic failure. I'm going to talk about mechanical alignment. This is one of my favorite videos out there that I have. Mechanical alignment. Now, what was tough here is I'm going to show this video, but I had to lay this red arrow on here, and I had to lay it in such a place that it could still stay on the video. So watch this closely. Everybody see that? I'm going to hope that people are shaking their head yes. I'm going to play it again. Watch the buildup. Container is not aligned properly. Literally shearing the billet. That's what you call a free billet skill. Talk about thermal alignment. If you have an externally heated container, there's nothing you can do about that because you have an externally heated container, but there's some things you should be aware of. When you preheat, when you are not extruding, you're going to align that container while the press is not running, which means your external heating is going to be on in the container. What is going to also heat your container housing. You're going to line it up, you're going to button it all up, and everything is all good in the hood. Then you're going to start to extrude on Sunday night. By the time the heat transfers, as you generate heat in the ID of the container, and then it starts to dissipate out, and then this ring here starts to basically come in, the container will start to become thermally saturated. But the other thing that'll happen is now the housing is going to cool down, because when you're heating the container with external heating, you're also heating the housing. By the time Tuesday or Wednesday rolls around, that housing is at a different temperature, which means the center point of that container is at a different point. Sometimes it's 2 to 3 times out of position from your regular alignment that you did when the container was cold and the housing was hot. Something just to be aware of if somebody comes back just a waggle on their finger. Quick and down and dirty and easy and simple, and I'm sure Richard's going to cover this, so I'm going to steal a bit of his thunder. Leave a butt on the back of the die. Then just measure its position. You can tell here that on this one, the butt is not actually into the center of the die. This is one where it's actually positioned properly in the die. Quick, down, dirty, and easy. You don't need anybody with lasers or piano wire. Just take the last die of the shift, throw it on there, pull it from there, leave the butt stuck onto it, and then have somebody check it and record it. It's a good practice. You should do it anyways, just to record. Clean out block. Let's touch on this bad boy. First one, clean out block must, cold clean out block must be run at room temperature. Another important part, y'all can't just take a piece of steel, hollow it out, put some clearance and cut this with a saw blade. These slits in the cold clean out block are calculated the size for the proper function, and this is a precision tool. It is a precision tool. This isn't something that you kick around and roll around and someone says, here it is, it's time to run. We are trying to treat this as a science now. The residual aluminum should be evenly distributed around the clean out block. Practice, pretty simple. The block should be weighed prior to running it through the container and recorded. If not, heck, just get your supplier to send you the weight. Once you pass it through the container, the block, the skull, and any little bitty pieces you've got, weigh them and record it. The skull weight should be graphed to determine if the liner and block interaction is correct. You can tell based on the look of the skull, if it's a tiara-shaped piece of aluminum, which I know that Rich is going to share as well, then you know you've got an issue. You know you have uneven buildup. If it looks like this, that's looking pretty sweet. And yes, this is somebody else's block because it's not about what we supply. It's about if it's getting a good clean out. This is good. This is good. This is good too. This one, maybe not so much. This one, it's like throwing a hot dog down a hallway. It's not doing anything. So if you're running a clean out block and it's coming out like this, somebody better be saying, what the heck? Because either there's too much aluminum and the clean out block's not functioning, or you're literally having no aluminum in the block, which means, or in the liner, which means all of the oxides that are on the billet are going right into the extrusion. And unless you're scalping every billet, which I don't think anybody is in aluminum, that's a problem. So what is this going to cause us? Pretty simple. If we take a look at the container liner and the amount of aluminum that's left inside the liner, during extrusion, that additional inverse segregation or buildup inside here of the billet skin will flow at different times through extrusion, and look where it goes. The only place it can, right into the profile. Clean out skull bad? Yeah, a little better. But still, look, this is a round tool going through a round hole. Why is there no contact here? This is a problem. And you can see we have a tremendous amount of aluminum here compared to this side. So, in closing, right? The maintenance tech today is more than someone who keeps machines running. Ask yourself, does the tool's reliability contribute to unscheduled downtime? Does the tool's diminished function affect scrap and productivity? As it starts to wear out, it's not like a light bulb. It doesn't go on and off. It starts to diminish. And as it diminishes, Is it affecting your scrap and productivity? I'm telling you, a soft container has to run slower ram speeds than one that's at a proper hardness. Does the tool's diminishing function affect contact efficiency? I would say. And lastly, does the tool's diminishing function affect ram speed? If you take a look at the tooling that we've been talking about, a shear blade, just pick a shear blade. A shear blade, the way that it functions in the first week or two that it's running, or month, or however your lifespan is of that shear blade. Once it starts to get on the end of it, why do we change it? Because we're starting to get blisters. Why are we getting blisters? Because we're pulling metal out of the die. Why are we pulling metal out? Well, it just needs to, it's a vicious cycle. So we have to ask ourselves, again, those questions. As all of the tooling, whether it be the containers or the dummy blocks or the shears or even the stems, does its diminishing factor affect those key points? So like David said, if you've got any questions or any concerns, or you want to call bullshit, I'm okay with that. Give me a call, shoot me a text, shoot me an email, and we'll do the very best that we can. I think that Lisa will have these this information so it can be shared with everybody at a later date. I'm just going to say, for me, this was cool. I don't mind doing it. Doing it this way. This is kind of cool. But thanks everybody for your time, and I'm done. Lisa, you take control. It's Richard now. Hi, Richard.
Thank you, Danny.
Bye, everyone. Peace.
Okay, hi everybody. I'm the last one up, so I'll try not to keep you too long. We're not that close to beer 30, so we should be good. What's my part about? What's this bit about? This bit here is going to be talking to you about some of the information behind what we're talking about. A little bit of billet metallurgy, this inverse segregation zone that Danny described as the bark. That was a rather good description. How the metal flows in the container and the impact that metal flow has on the way the dies run, and how alignment impacts the metal flow in the container. Also, I want to talk to you about the loads involved in extrusion. Really, what I want to try and get across to you is the why alignment and preventative maintenance is important. Danny made a really good comment about dummy blocks. Dummy block on an 8-inch press costs you around about $1,000, give or take a little. If you have a stoppage during the week and you're fully loaded and you lose the press for a couple of hours while you heat up a new dummy block and then you change it, not only is it a pain in the butt for the maintenance people because they happen to be running under pressure and doing stuff, it's going to cost you more than that $1,000, substantially more than that $1,000 for a new block in down press time and lost productivity. And we need to be thinking about this. Now, if we change that dummy block out every week, not just take it off and look at it, change it out, put a new one on straight away every time we have our shutdown. We can take it away, clean it, put it in a rack, use it again. If we do these things, life is easier because you know that at a certain time on Saturday, if that's that particular press, or a certain time on Thursday, if it's a different press, you're going to do a dummy block change. You put a block in the oven, number of hours in advance, the press is down, you go up there, you do the dummy block. No stress, no pressure, and most importantly, no lost production time or lost money. And that's some of the things we're talking about when we mean preventative maintenance. But let's start off a little. Let's look at our load on our tooling. I've taken for an example here a 3,500 ton press that I was working with in Newcastle in England, in Burtley. It was a 9-inch press. Yeah, a rather powerful beast. We were trying to visualize just how much load 3,500 tons is. Well, if we take something we know, which is the base model Toyota Tundra truck, the V6, it's about 19 foot long and it weighs 2 tons. So if I want 3,500 tons, I need 1,750 Toyota Tundras in a line. And if they're all touching bumper to bumper, that is 5.7 miles of Toyota Tundras. Just try and think about somewhere which is 6 miles away from where you are. Take a line of Toyota Tundras touching each other bumper to bumper and then stand them up on their end. It's high enough that it's a hazard to aviation because internal flights at 32,000 feet would hit it. Think about when you look up on a cold, crisp winter's day, which is looking like it's going to be pretty soon. You look up and you see those contrails from aircraft going over. It's a stack of trucks as high as those contrails, and it's all sitting, in this particular case, on a 14-inch disc of steel. And to make it better than that, some idiot's cut a hole in the disc where the aluminum's going to come out. So it's not even a solid piece of steel. The loads on the tool set are enormous. And that's why when Danny was talking about pressure rings being flat and straight, pressure plates in the back of behind the stem being flat and straight, these things are all really important because any misalignment in here can cause an enormous change in the way the pressure is distributed. And I have an example of that for you in a moment, a real life example. But if we say we were to put a wedge in under here, then this side would take very little pressure and this side would have much more pressure. And you can say those bolsters, hell, they're H13 steel. They're 1.5 feet thick. They ain't going to bend. Well, I can tell you, a stack of Toyota Tundras, 3,500 foot high, that'll bend that tool. That will damage it. It will dent it. You can coin the front of the container. You can do a lot of damage with these things. And here's my example. This is taken from an ET paper, 2012, from Pavel Kavanowski, who was working for Wafer at the time. This is a die plate for a GM bumper die that was running at the hydro facility in Holland, Michigan. And you can actually see down here, I think fairly clearly, there's a crack in the die plate. And there was another crack up in this corner. And you can see where we cut it out to do some metallurgical investigation. We found there was pretty much nothing wrong with the tool steel, which was a bit of a surprise. There was a lot of hooing and hawing and scratching of heads, but this die life was down dramatically from the normal die life. And you could see it happened at a particular day. After a particular day, there was a drop in die life. And we spent some time chasing it, and in the end, this was it. I actually took this picture. This is about the size of a nickel. It happened to be in exactly the right position to put the die plate into a teeter-totter and create the stresses which caused those dies to crack. I remember at the time people telling me they thought there was this, and I had to call BS on it. I said, no way, I'm sorry, I don't buy that. And so they cleaned it off and the die life went back to normal. And so I'm a convert. That was about the size of a nickel in the tool stack, and it caused enough twisting that in that one particular case, which I suppose was a perfect storm, it cracked the die, and it cost many, many thousands of dollars. And once it was cleaned off, it was done. And that led us to do an audit of the remaining bolsters to find out how many were perfectly flat, how many were perfectly parallel, were they in tolerance and dimensions. And we ended up having to buy some new bolsters. But it did improve our die life and our production. So, preventative checks. And I refer you to the webinar, which is on the AEC library, which was Chris Jarrett and I, a few years ago now. We did a webinar specifically on just alignment, so I'm not going to beat too much of this. But the recommendation was the pressure ring in the platen should be checked, flatness every 6 months, and you should have a tolerance. And Al Kennedy on his website's got all sorts of numbers about what these tolerances should be. The bolsters should be checked yearly, that they're not coined. We found a bolster that when we put a steel ruler over the flat face that was normally in contact with the backer, we could flick quarters underneath the ruler in the middle. The bolster had dished so much over years. And so I asked how long since this bolster was checked. And it turned out the bolster had been in the plant for 12 years and had never been looked at once. That's not a situation we really want. We need to make regular checks. Next, we need to check the die stack to the container alignment, what Danny said about leaving the butt end on, and we'll look at that a bit more in a second. That should be done daily for regular extrusion. And I have to say, if I was running automotive, I'd be tempted to do it every shift. It doesn't take any time. You just leave the butt on. You take the die out, and when it's cold, someone measured it. It's a fairly simple procedure. The clean out block, well, you should always run that with alloy changes, so you don't contaminate alloys with the previous alloy that was in there, and you get a free check between the stem and the container. And I'll a little bit more about that in a second. But don't forget the pressure plate that sits behind the stem. That's the bit people forget to check. That needs to be checked as well yearly. And all these things need to be aligned, clean and parallel. Now, this is what happens if we don't do the preventative maintenances. This is the 7-inch press in Hydro Extrusions, New York, up in Ellenville, back in about 2005, I think it was. I was involved in the analysis of what had happened. You can see the dummy block. It's just entering the container, so we know we're at the start of the push when the press was at maximum load. The dummy block just, the stem literally just exploded. And the piece of steel that was in here, this scallop that came out, it went a substantial distance over here. Luckily not meeting any soft, fleshy things on the way. So there was no harm done to people, but it easily could have done serious harm. We went and we looked at this and we were trying to get some sort of, sorry, I'm just distracted, some sort of check on what went wrong here. We found it was root causes were poor alignment. Metal had built up on the side of the stem, and they knew it wasn't right, but they'd let it tolerate it. They'd lived with it. In fact, you can see on the edge of the dummy block here, you can see some of the metal building up. They wanted to get rid of this in a hurry because they had visitors coming from head office. So someone took a torch and tried to get the aluminum off, kind of get it hot and scrape it off so it didn't look so crappy. Unfortunately, the torch rested for a little too long in a few spots and softened the steel. There was no stress relieving practice for the stem, and so over a period of time, a crack grew. And that in itself wouldn't have been too bad because we could have seen the crack like the picture that Danny showed you, except that we still had the poor alignment to the stem and the container. And that meant there was aluminum smeared all down the side. The aluminum was smeared in the same place that it was smeared before, so the same place where the torch had been, and that aluminum hid the crack. So the first thing the crew knew was bang, and pieces of hot steel flying in all directions. Not a healthy situation. There were so many opportunities for this not to happen that they really had to work very hard to get this to happen. If you check your alignment, that keeps your stem clean, so you don't use a torch. But you never, ever use a welding torch or a hot flame on any load-bearing piece of steel on the press. These are highly precise pieces of steel with good metallurgy, who've been heat-treated carefully. So, alignment. I remember many years ago, I asked a maintenance guy when I was working in Banbury Extrusions in the UK. I said, what's the alignment on my press? Oh, it's good. And I thought to myself, what does that tell me? It actually tells me he's got no idea what the alignment of the press is. Because if you know, you can express it in numbers. And I quote from Lord Kelvin, and this is one of those beautiful bits of English understatement, which I just love. When you measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. So if someone tells you the alignment's good, or you're tempted to tell somebody else the alignment's good, that's not acceptable, folks. The alignment should be a number. It's 10 thou out to the northwest, or it's 5 thou up and 6 thou right, or something like that. You need numbers, and when you have numbers, you chart them. And with that chart, you have a direction in you know where things are going. You know if something's drifting and changing. So if you see your alignments out 4 thou, 6 thou, 8 thou, you're still well in tolerance, but you can see it's moving. Now, you can say, okay, next time I'm down, I'm going to try and find out what's causing that movement, what's causing that drift, and put it back. That's so much better than it going out of alignment, making bad products, and everyone's screaming and hollering, and maintenance is blamed for everything as always. So this brings a level of calm if we can measure things. Right, let's look at a little bit about the flow of metal in the container, and we'll start with the billet. And if you've never seen it, that's what a casting table looks like. Below each one of these little arms is a log being produced vertically, and this is what they look like when they come out of the casting pit. They're about 288 inches long. And to be honest, these two guys, if they were working for me and stood there, they would have got their butts kicked severely. Even with a big steel frame, that's not a safe place to be. But this was staged for a nice photograph, and frustrates me, but photographers think that's a nice photograph. But that's what the logs look like. If we cut a slice from one, and we cut a slice from the slice and a little piece, and we look really tiny right down here in the outside edge skin of the billet, we have this inverse segregation zone that Danny mentioned. If we plot the chemistry, that 4 thou area there on the surface, the chemistry is much, much higher. The silicon's 4 or 5 times higher. The iron's 5 times higher. So the chemistry of this layer in the surface is very different. It flows differently. It melts at a different temperature for tearing. And most importantly, if you're making building sections, it anodizes a different color. So it can look pretty good when it comes off the press, and when it comes out of anodizing, it looks like it's got tiger stripes. So we want to control the flow of this inverse segregation zone. Now, the size of the inverse segregation zone depends a lot on the casting technology of your billet supplier. These are 2 most common casting technologies visible in North America at this time. The top one here, hot top, or known as Numax or MaxiCast from Wagstaff. The inverse segregation zone tends to be bigger, and notice the black patches in here, there are more of them. It's also richer. This is the gas slip, Wagstaff air slip, hydro gas slip. It's a much smaller inverse segregation zone, and it's not as rich. So we don't have as much of this, which I'm going to call the bad stuff, if you get gas slip or air slip technology molds. We have more if you have Numax. Why do people use Numax? It casts certain alloys better if you have some harder alloys to cast, and it's about half the price for the table. And so if you're buying, sorry?
Richard, it's Danny. I just want to jump in here. This inverse segregation zone here, and the size of this inverse segregation zone is very, very, very critical in high tensile strength alloys, not just because of the amount of bark, I will call it, that's on this, but we typically use less clearance between the OD of a block and the ID of a liner in the higher tensile strength, or even softer alloys again, because they have a smaller area of which they can be extruded. So an alloy or a log that has a larger inverse segregation zone, we find can interfere with the interaction between the OD of the dummy block and the ID of the liner, because we can basically actually end up extruding part of this that will show up as the surface defect.
And the inverse segregation zone is really not our friend.
No, I just wanted to jump in and add that, sorry.
Oh, absolutely. No, thank you, Danny. Please interject. Here's a little just diagram. This is a graphic. There's no intention the scale to be right, but the red is intended to be the inverse segregation zone. And when we have a long billet, what's happening is the aluminum is flowing from left to right, and then it goes up through the reduction cone to the die. It tends to try and drag some of this material with it. This is called type A or front end inflow. The rest of this layer is plowed up by the dummy block and ends up in the middle at the back. Now, if you're making automotive sections, this is a major weakness, or something which is going to be machined. This is a major weakness. If you're making window frames, it's not such a big deal unless it's very pronounced. The inflow at the front, the type A inflow, this is a real big deal if you're making window frames which are going to be anodized. So it depends a little on your market, which is the more serious. The big trick to controlling the type A inflow is to make sure your container liner temperature remains stable. And this means you have to be able to suck enough heat away, and I'll come back to that in just a minute. Here's a little experiment. This was done by Hydro back in the 90s. They took a billet and they machined off a little bit, and they replaced the inverse segregation zone with thin foils of alloy of unknown chemistry. And the reason for this was the chemistry chosen. It had the same flow stress as the other aluminum at temperature, but this material, when it was anodized, came out jet black. So when we cut a billet up, we could anodize it and we can see the blackness. So this is the flow of the inverse segregation. Here is that type A inflow occurring at the front. And here is the type B inflow plowing up with the dummy block at the back. And this is 67% of the billet extruded. So that means on a 21-inch billet, we've got 7 inches to go. As we progress through, you can see that the type B inflow makes it into the section about 15% prior to the end of extrusion. So there's no way you're going to stop at this point and shear the butt off. Nobody's going to make you a dummy block that will, a butt shear which will shear a 4 or 5 inch butt very effectively, particularly in stronger alloys. But it's not yet reached the point at which I would call it coring, because this is really, really exaggerated because it's an anodized up jet black. But you see here the type A inflow is getting stronger. And as we get down to a 10% butt, now you can see if we had a cavity up here on a multi-cavity die, that would be in it. That would be in the surface of our material. Inverse segregation zone would be there. And when it's anodized, it will come out a different color. And we will be making scrap. So this inverse segregation zone and the way it flows is very important. And a key part of it is controlling the container temperature. And the container temperature is also very important in the metal flow. When we have a great big long billet, we have metal that is stuck to the side of the container, and we are pushing aluminum over aluminum. Subject for another day. It's a long discussion, but aluminum never slides over steel. Aluminum sticks to steel, and then aluminum slides over the aluminum that is stuck to the steel. If aluminum rubbed on the steel, we would wear away the steel in no time at all. Very, very strong chemical attack if that happens. So the aluminum bonds to the steel, and what happens is at the edges, there's all this friction holding back the flow. And you can see here, the flow is faster in the middle than it is at the edges. And of course, we're generating a lot of heat because we're rubbing friction here. And most of the press power goes to heat. So force times distance, and that's thousands of tons times maybe 2 or 3 feet, all gets converted into heat, and that heat has to go somewhere. But at the start of the push, the aluminum has a pretty relaxed way that it can create the reduction from, say, 8-inch billet down to a 2-inch profile. This is the natural reduction cone. This forms. As we proceed, and we get down to a point where the natural reduction cone is now bigger than the distance left in the billet. Now we start to force the way the reduction occurs. And this can lead to changes in the shape that's coming out. And this is where we can get front to back variation in our shapes. And when we get really close to the end of the stroke and we're just short of the last little bit before the butt comes, you can see we're totally constrained. It's a totally different environment. And that's why you'll often see a little leg at the end of the extrusion do this sort of wave. Hopefully in the scrap section, you're going to lose to stretching, but I always call that the section waving goodbye. Alignment has a big impact on this. If we're out of line, it amplifies everything. So this is what Danny was talking about. It's the die with a butt on it. You measure your north, south, east, and west. You can calculate from the 2 Y measurements, the 2 X measurements where you are, and you plot a graph. This is a key part to using the information for preventative maintenance. 1, you have numbers, not just good or bad or great today. We have a number. It's 14 thou up, and it's, what's that about? Oh, no, it's about 8 thou up, sorry, and about 6 thou to the left. Now you have an action plan. You put control lines on. In this particular case, that control line's at 30 thou. That's the line that says, if I cross this line, or I look like I'm going to cross this line, which I'm pretty sure this Y one's going to do very soon, something systematic is occurring here. We need to look at this. Let's not wait until it breaks the control limit to do something. Let's be proactive.
Hey,
We
Richard?
can prevent problems. Yes, sir.
Just to jump in here, this again, it touches on like what I mentioned earlier, and a lot of the things that we do overlap, and that's what makes this awesome, is again how I mentioned the container positioning from a Sunday night or a Sunday when a container is aligned to, you know, possibly a Tuesday, Wednesday, Thursday. Would be interesting to do that several times and look at the plot of when that dips and doodles and moves around.
Oh, I mean, I've worked with one guy, and he used to do his maintenance checks on a Sunday, and he'd do his alignment, and I'd come in and he'd say it's good, and we had our discussion, and we got down to it's 5 thou, great. So then I'd leave a butt on in the midweek when I was visiting the plant, and it was always out by about 40 or 50 thou. And that was it, and that I didn't know what it was. And in fact, I spoke to you at an AEC full meeting over a beer, and you drew out the sketch for me and showed how the container rises up when the external heating's on. And I thought, oh dear, how many years have I been doing this and I didn't know that? So these things come in, and this is a big thing about externally heating containers.
Yeah.
And I'll come back to those and just saying, oh, I think I jumped a slide. There we are.
Yeah,
I'm going to run a little video now. So Danny you're not the only person running these things, Danny, right? This is my little animation, and I want you to see the effect of the cleanup block. And for some reason, it hasn't started at the beginning. Let me just rewind it. I apologize for that, folks. I was dry running it to make sure I got it right and forgot to reset it. So here we are. This is us looking at the extrusion going through the container. And we're looking here theoretically up the press with the die removed. And you can see that the dummy block is coming perfectly down the middle of the container, and it leaves a uniform skull all the way around the inside. So when we run our extrusion now, and by the way, this graphics guy, he really does love his burp cycles. I noticed Danny has the same issue. That's a burp cycle and a half, that is. But so we run our extrusion, and the dummy block expands and leaves behind that layer inside the container. Now, when we bring up our cold cleanout block, which is pristine and clean, because I totally agree with Danny, it's a precision tool, and it's carefully loaded and pushed through, it will bring out a uniform skull all the way around, and that's a crown. Now, we run through the same process now with a press where the container is high. This could be because of the heating elements, or it could be many other reasons. But we go through, and now you see it's thick on the top and it's thin on the bottom. So running our extrusion, in fact, in this particular case, it's not just thin in the bottom. The dummy block is gouging against the steel of the container. And in doing so, it's wearing the dummy block and it's wearing the container. Those are pieces of steel that should never touch. When they touch, they cause wear. I have lots of dies that people have sent me with inclusions in them that turn out to be pieces of dummy block and container. And because there's no contact has been made between the dummy block and the bottom of the container, you can see we've formed a tiara and there is no aluminum here. And this is a situation which is not good. So I use the same slide as Danny. This is what Jeff Bourgoin put into the die committee booklet a few years ago. And for me here, this is a great opportunity. I was always thinking, how do I measure this with numbers? Because I don't want to have meager and unsatisfactory knowledge. And what I do is I measure the angle of the Pac-Man. This is Pac-Man mouth open. This is Pac-Man mouth closed. This is probably, I don't know, 30 degrees. This is about 120 degrees. I measure it. I put it on a chart. I say, if it is 0, tick box, everyone's happy. If it's up to 45 degrees, then I will deal with it when the press is next down for preventative maintenance. We'll take a look at it. If it's 130 degrees or greater than, say, 60 degrees, then I'm afraid this requires some more immediate attention. Because we are here in this top left-hand picture, we have serious steel-on-steel contact occurring where the dummy block is running down the container. This will wear the dummy block and then maybe lead you to attempt to weld it up. And it will also gouge out the container, which will lead to bellying, both of which Danny has showed you is not bad. You can also see here clearly, as Danny pointed out, this is much thicker here because that's where all the aluminum is. This is also going to affect the way type A inflow occurs. You're going to have a lot more difficulties and problems with type A inflow with this misaligned press. added to which all of the inverse segregation zone and everything is being dragged into the process here while some is being captured in the press. The second thing I would do with this is I would take a knife or a chisel and I would remove the skin, or weigh the block before and weigh the block afterwards, and I would weigh the skull. That tells me that I now know the average thickness of this layer. That tells me how my dummy block is expanding. If I plot this over time and keep a record with it for each dummy block as it comes back to the press, I can watch that creep that Danny talked about. I can predict when the dummy block is going to come to an end. That means it doesn't come to an end on night shift at 3 in the morning on a Tuesday, when that famous thing goes through the tannoy, maintenance, press number 3, maintenance, which is really what you want to hear at 3 o'clock on a Tuesday morning. If we can do this predictive stuff and have action plans based on data, we don't have to do that anymore. We also don't lose those hours of press downtime. So all our figures look better and our profitability is better. Now, the final part of the alignment thing, which is really important, is we're making, this is our dummy block pushing our aluminum through the die on the right. A lot of heat is generated between the friction between the aluminum and the aluminum sticking to the container liner. Excuse me. About 30% of it goes into the container and about 70% of it comes out of the press as increased exit temperature of the aluminum. Now we need this because we need to hit exit temperature. That's really important. We need to be up around about 1,005, 1,030, that sort of level here at the exit to get really good quality metal. But if we could take more heat away into the container, two things happen. One, that lowers the temperature very much locally here, and this constrains that type A inflow. If we have a container and it's been externally heated over the weekend and the whole piece of steel is hotter than 800 degrees, where's the heat going to go? It's got nowhere to go. So we end up with a lot more flow occurring in this area. And on Monday morning after weekend shutdown, my presses back in 93, externally heated, used to have terrible, I mean awful surface. And it would take the best part of a day for it to sort itself out. Now you can get containers with heating elements inside, much nearer the middle. This is much better. But I have to emphasize, the nearer those heating elements get to the middle, the better. Taking them from the outside to halfway is a good step. Taking them halfway to closer to the liner is a much better step. You use a lot less heat. There's a lot less saturation in the container. And this also means you can suck more heat out very early on after your startup from a shutdown. Finally, if we can suck more heat out through here by having high conductivity steel, there seems to be a marvelous battle between North American container makers and European container makers. The North Americans are using high conductivity steel and understand that a container is to do with getting heat out. It's a thermal mass, it's a stability item. And I'm not saying this is just Danny's here, Thumb Tool do the same thing and other people do as well. They use high conductivity steel. I don't know the difference between them in fine detail. But in Europe, they're using H11, which is a low thermal conductivity steel, and it's strong. And you get this, but it must be strong. Well, I've asked Danny, I've asked Thumb Tool, I've asked other people with liners. The Castool design and the high thermal conductivity steels, they don't break. So there's no point in being too strong. I mean, that's like saying I want to make my Ford truck really strong. Let's not make it of aluminum, we'll make it of 1/2-inch steel plate. Then I've got a Humvee and my fuel economy goes down the toilet. We need right things for the right courses, and getting heat out of here is important. It's controlling the temperature, it's controlling the flow. So the container is a very important part of this element. Now then, there is an impact of poor alignment on productivity. If we make the wrong shape, it's scrap, right? So what happens if the die isn't where we expect it to be relative to the container? That slow moving metal at the edge of the container, the die designer has taken it into account when they design the die. But if the die isn't where it's supposed to be, now we have a piece of bearing which is supposed to be in a slow area, and a piece of bearing which was designed for a slow area is now in a fast area. The shape goes to hell in a handbasket. And if the container is hotter on one side than the other, that's thermal alignment. Also, the shape comes out wrong because the side that's hotter will flow faster. And the solution to this, because this has been going on for a long time, is people buy very conservative dies, smaller ports, feeder plates when they don't need them, bigger bearings, because it can iron out the impact of these upstream problems such as alignment. But the cost of this is low productivity. You get high shape stability, but you got low productivity. And my experience hanging around extrusion plants for way too long is that the conservatism that is built into these dies, because of alignment and because of thermal saturation of the container, etc., can cost you at least 25% of your productivity. And I've had people look at me, BS. And we've got the press lined up and we've got things sorted out, and let's try running faster. And just doing a couple of simple things, not attending to everything, you've got 10-15% just there, sometimes more. The other problem is, not only is it holding you back from where you should be today, but it's also stopping you going where you could be tomorrow. You lose your opportunity to run more open dies, to open up the ports. Now, there are several webinars on this that I did with Rick Liscombe over the years on die design and productivity. They're also in the AEC catalog. But I want to show you this one because this one is particularly right now very close to my heart. This is a pressure limit diagram. The left-hand axis, the y-axis, is speed. Can be ram speed, extrusion speed, I don't mind. The bottom axis is billet temperature. And if we try and run a cold billet really fast, it can't do it. The press just hasn't got the power, the force to be able to make this happen. So we get limited, and that's the blue line. And as the billet gets hotter, it gets easier to push and we can go faster. Yay, we're on a good one here. It gets hotter, faster, hotter, faster, hotter, faster, hotter, faster, till suddenly we reach this point where the exit temperature is now too hot. It's tearing, it's melting, bad things are happening. So we hit the red line. The red line is what's limiting our exit speed, our extrusion speed, by virtue of surface tearing and exit temperature problems on the press. So now I get to this, I run my billet temperature up, I have to slow down, I have to slow down, I have to slow down. Well, we all want to run where this green dot is. Hey, it's pretty easy, right? We work out the limit diagram for this die on this alloy on this press because it is specific to a stroke number, an alloy, and the press to do this calculation. I want to be here at this green dot, and I know where it is, and I set my press to run it. Now then, my billet oven is turning out billets. I'm asking for a 470. What do I get? Sometimes I get a 480, sometimes I get a 460, maybe occasional 450. There is a range of temperatures coming out of my billet oven. And I'm going to put that here, and I've chosen a deliberately bad one for the purpose of example. But this is a billet oven here, kicking out a wide range of billet temperatures from what I've set. Now, if I change that into a line and I run it up to where my dot is, it's telling me that my colder billets that come out during that process, the press doesn't have the power. On the hotter billets that come out during that process, the surface is going to melt. So now my press operator is going to be seeing, I've got it a third of his billets are running good. A third of the billets, the press is struggling, low acceleration, the shape at the beginning isn't good because it's not up to speed, and the other third is tearing and it's scrap. I can tell you that press operator isn't going to run that press like that very long because we train our press operators, our press drivers, to be averse to scrap. They will slow down to this point so that all the billets, the whole range of billets that are coming out of that oven will all produce good material. And this will be instinctive. They may not even be conscious they're doing it. Now, I give the guys at Granco or Belco or Omov or someone a ring, and they come out and they give the oven a good service. And by this, I mean make sure the door isn't leaking. Make sure the insulation's in good shape. I just check the whole thing out and sharpen the thermocouple probes, check the control systems. And we now get...
Richard, can I jump in here?
Yeah.
Yeah, when you talked about sharpening the thermocouple probes, there's a couple of other things that are really important about that is most of them, with the probes that are coming in and touching the billet, there's two of them. It's important to A, make sure that they're the same length. B,
yes,
make sure that they're cut on the same angle. You know, for $20 worth of steel and a bench grinder, you know, sharp is sharp, I get it, but consistent is consistent. If you have one at a 45-degree angle and one at a 65-degree angle, you're going to get
absolutely.
you're going to get different depths, different readings. So if you've got 3 zones, 6 thermocouples, or 4 zones and 8 thermocouples, you don't want 1 degree variance in angle cut as well as a quarter. You could have one touching and one not.
Excuse me.
You know, you can have one thermocouple touching and one not even touching. I've seen it. I've got pictures that I've shared in other press maintenance things where
I've seen them come up like this. One's long and one's short, and one gets pushed all the way back and buries deep in and makes a dent.
Like you and I standing beside each other, right? Or that's more like this. But anyways, they you know, consistent, right? Consistent. Anyways, I'll jump out again.
Sure. And what Danny's also saying is very important. If you sharpen your probes a little bit like you would a pencil, you can end up with striations running around the probe, and that causes the probe to pick up aluminum. So it needs to be reasonably well sharpened. But here we are. Here we have now our good distribution coming out of our oven. Our oven's been serviced. Our probes are in good shape. Everything's good. See how much more productivity I can get out of my press purely because I have good temperature control in the oven. And this can be really a lot. Again, we're in big numbers here, and this is worth considering. So it's not just billet temperature, though, it's all the temperatures: container temperature, die temperature, exit temperature, your quench. All these things add up to our process. And quite often they're not lined up. Just lining them up, getting the averages in the right places is important. Whole webinar on this, again in the library, was done earlier this year. But what happens is your sum of variances changes dramatically. If not only lining them up so their means are in the right place, but we also reduce the distributions, we reduce the standard deviation element. Now we really get a much, much tighter process control. And that gives us the opportunity to run better production, more productivity, but it also frees us up to go forward into the future using more open dies and getting our presses to run much more like a sports car than an old truck. And I like that analogy because an old truck, if my wheel alignment is out by ½ degree, I really don't notice. It doesn't affect the ride of the truck, and probably the way I drive it, I wear the tires out quickly anyway. But if I'm driving a NASCAR and my alignment on those front tires is out by ½ degree, about halfway around the 3rd lap, my tire explodes. So as we are moving into a more and more challenging extrusion environment, people are taking on more and more automotive. In regular window sections, 0.5% customer returns is considered pretty damn good. In fact, we're good if we've got 0.5% customer returns. In automotive, if I get returns of 10 parts per million, I can lose the contract. I worked with Toyota once. They wanted less than 5 parts per million to be returns. That's a hell of a change in quality standards. But even in building systems, people want thinner walls. They want tighter tolerance gaps. They want everything better every year. So what was good last year? What was good 10 years ago? What was good when I first started in extrusion? It ain't good no more. It isn't going to do it. It isn't going to cut it. And here's some stuff I've got from Rio Tinto. Thank you, Jerome, for letting me use this. This was some work done by Chris Jowett and me back when I worked for them in the late 80s. And it's looking at the difference in sharpness and size of probes on the temperature they read from a fixed block. You can see as the probes become less sharp and they gain more mass, they respond more slowly and they reach a different final temperature. Now, this was one particular set of circumstances. Don't take these numbers as what it would be like in your billet oven. But the point is, as long as your probes are sharp, smooth, and everything else is lined up correctly, as Danny says, they'll give you a good reading. And there'll be an offset, but that's easy. The oven manufacturer will build that offset into their control system. But when the probes start to get blunt, they don't penetrate the oxide layer on the billet as well. You don't get such an accurate temperature reading. They build up aluminum. That encases the mass of the probe again. And we start to get under readings. Well, what happens to the control system in the oven? The oven starts turning out hotter billets and hotter billets and hotter billets. And if you're only changing them once a week, I have actually seen an example where I could see the productivity of the press start to drop after about 3 days. and it would pick up again on the Monday again after the probes had been sharpened at the weekend, because the billet was getting so hot that we were hitting the right-hand side of that limit diagram. So you really need to consider very much frequency of sharpening probes. For me, daily is a minimum for any extrusion plant, and each shift for automotive. And you also want to be verifying what you're seeing. This is a technique Johnny Pangborn presented at ET 2012. It's just two open thermocouple wires, and you can see where he's done it several times in the surface here. He puts them on the billet and he hits them with a hammer. They give a very accurate reading. There's no mass in these, and they're in good contact totally with the surface because they're being hammered in, and it's very quick. And I can recommend you to have a look at Johnny Pangborn et al.'s paper from ET 2012. Having done that, what do? We have a number. We put a number on a chart. So I asked, this isn't an absolute, this is a relative. I asked for a 470 billet. This one is above. So I put down a +5. I got a -8. I can't see what the numbers are, but you can see here consistently, this oven is turning out that it's colder than I'm asking for. We now have information. This isn't the old maintenance, press 3, the oven isn't working, which comes over the tannoy system. This is a quiet moment in the maintenance room over a cup of coffee saying, guys, I think we've got a bit of a problem here. And there's even, I would say, a bit of a downward trend going on here. Our billet oven is not kicking out the temperatures we want. We've not yet reached a control limit, at least I hope we haven't. Can you take a look at this when we have our next PM downtime? Isn't that so much of a better world than just getting blamed for everything and getting chased for everything? So this comes down to what I'm saying. You measure numbers, you chart them, you trend them, and you act upon them. And I think really that's 3 people have said the same thing to you. We've all more or less said the same thing. And there is a wonderful Russian proverb, which is "Dovodny no provadny," which was made famous by Ronald Reagan. And that was what he said to Gorbachev. I trust you, but I need verification on weapon systems and things that were being done in their negotiations. And because it was a Russian proverb, it was a very powerful thing to Reagan to say to Gorbachev. I doubt if you thought you were going to hear Ronald Reagan quoting something in a webinar on press maintenance, but there you are, full of surprises. So my summary: use data to predict failure. Use data to predict when you need to replace something before it becomes a scrap generating or equipment damaging thing. Do regular checks on all process measurement stations. Those billet probes, if you're not cleaning them and checking them, they can be lying to you. And that can be a systematic problem which can lead to some terrible scrap. Do regular checks on all loaded components, such as that pressure plate that sits behind the stem. Notice I use the word regular, not frequent. Regular is once a year, once every 6 months. Frequent is what I want you to do with container to die alignment and stem to container alignment. That should be at least daily. Do routine plan swap outs. Dummy blocks. Danny showed you how the life of a dummy block changes, how through its life that gap starts to open. And once it starts to go, it rushes. Well, if we take it out every month, take it apart, clean it, check it, maintain it, reassemble it with appropriate mild lubrication in a few places, we found in experiments that I've been involved in that we can increase the life of the dummy block significantly. But most importantly, as long as we've made our measurements right and using our data right, we can be pretty damn confident that when we come back on the next maintenance time in a week, that dummy block is still going to be running. And we haven't had the press 3 maintenance dummy block change occurring in the middle of the night shift. The same thing for shear blades. Once you're doing it every week, it's amazing how slick you can get at changing that blade, or you can get the Castool system with the removable edge. But once you've worked out how to do it, and you're doing it on the maintenance downtime, you're not losing the company money from lost production. And that money from lost production, you can then work out what you've saved, and you can go and use that to beat up senior management to get more money in your budget. Create a plan to stay on top of your equipment. Don't let your equipment get on top of you. And please, for as much as when I was in a plant, I used to holler at maintenance, I always understood they are a most valuable resource to extrusion. It's not just that you fix things that break, but because you have the capability of keeping the operation running at peak performance all the time by fixing things before they break. Collect data, chart it, use that data to predict and then act upon those predictions. And there's me with a slightly smaller beard and a damn sight darker than it is now. The sun's shining on it, so it's looking even whiter than it was before. So that's my contribution, folks. I also overran. I think all three of us managed to overrun. I believe now, Al, over to you, sir. With us, Al?
Thank you, Al.
Hi, Al.
Have I got it now?
You've got it, buddy.
I just want to show 3 slides
Yes,
very
you did.
quickly. We've run long, and I want to point out, first of all, that the press maintenance manual is now free online. This is the website. Have a look at it. Keep this in your reference. Free online for you and all your people. Second, I'll mention that it does contain master maintenance schedules. As you see, they look a little bit like the maintenance schedule for your car or truck. Items marked as daily, weekly, monthly, quarterly, and different intervals. And they're also sorted according to everything that should be done daily and everything should be done in other increments. These files are available as Excel spreadsheet files, and they may be downloaded at this location. Again, it's all free. Make a note of this, and if you do not have a maintenance schedule system, this may be a good place to start. And because they're on Excel files, they may be customized to fit your own equipment and your own experience. But it's a good starting place, and it makes it very easy for you to create your own regular maintenance charts. Hope you've had time to take a note of that. And if you have any questions at all on these or any other subjects, feel free to give me a call or an email. I'm retired and have time now to listen and try to help you find an answer. These are my contact information points. We had intended to leave time for question and answers, but because of the presentations running long, I'll suggest that instead you send your questions to any of us who have left our contact information, or send them to me and I'll direct them to the right people. And we'll try to get answers back to you. And I thank you for attending. I appreciate your patience. Been very good information, and I'm sorry that we did run long, but I think it's well worth your time and ours. Thank you. Back to you,
everybody.
Listen.
Thank you.
Bye, everybody. Stay safe out there.
Thank you all so much. That was a lot of very valuable information, and we appreciate it, and I'm sure our audience does too. Thanks, Al, for the information you provided at the end there. Thank you for being the leader of the press maintenance group and events and webinars and what have you. We have recorded today's webinar, so it will be posted in the AEC library soon, probably within the next 24 hours or so. And of course, as always, we're sending out an evaluation survey, and we ask that you please share your feedback with us. It's very important to us. We do take it all under consideration, and it helps us to develop future webinars and also bring you speakers and topics that you want to see at the live events. We are developing our 2021 calendar of events, and those should be hitting your desks later this year before Christmas. But always visit aecmeets.org to read up on the latest details on upcoming events and to register for webinars and live events. Our next webinar is going to be on November 11th. Where Craig Werner and others will be talking to you about the AEC LMS, better known as the Learning Management System. And this is a wonderful tool to train new employees And we'll be teaching members how your management can use this platform to benefit the new employees and your workforce. Our November 18th webinar on Chrome, which will be presented by Scott Wojciechowski of BCI, is being rescheduled for December 9th due to some constraints for Scott that he is unable to do that on November 18th. But it will be, we will be ready for that on December 19th. Again, watch aecmeets.org. We have lots of great webinars and events planned for next year. And of course, we are moving forward with ET. So this is going to be the big 50 years of ET celebration in Orlando next May. Online registration for the event and the hotel booking site. As always, it has been a pleasure to bring you the information and programming that you are interested in. I'd like to thank everyone for attending and staying with us for today's long webinar. Thank you to the presenters. Al, thank you all again for being with us today. And we will hopefully see all of you soon.
All right. See ya.
That's all I've got for today.
Thanks.
Bye,
Take care.
everyone.
Bye, folks.
Namaste.
How do I get out of here? Right.